Hello, everybody, and welcome to our 25th Inspiration Exchange session. My name is Fergus Imrie, and I'm a postdoc in the Schaar Lab. And I'm delighted to be hosting today's session on causal deep learning. Today's session is going to be formed of two parts. In the first part, one of our PhD students from the lab, Jeroen Berrevoets, is going to give a presentation introducing causal deep learning and presenting our lab's roadmap for this field. In the second half of the session, I'm delighted to welcome three guests from industry: Dr Cheng Zhang, Professor Guillermo Sapiro, and Dr Simon Woodhead, who are going to join us for a panel discussion. And after this, we're going to open up for a Q&A session. Please do feel free to ask any of our panelists or presenters questions about anything related to today's topic. And please put your questions in the Slack channel, which we'll post in the chat now for you to join. And we'll try and get through as many questions as we can. As always, the earlier, the better to post in the Slack channel. Without any further ado, I'd like to pass over to Jeroen for his presentation on causal deep learning.
This presentation is largely based on a paper I've written with Christoph, Zhaozhi, and Mihaela, of course, my supervisor. And that specific paper has been sent to you all recently with this email that the lab has sent out for this specific Inspiration Exchange. But in the past, we've also discussed causal deep learning in previous Inspiration Exchange sessions, although those were mostly introductory. And we've also written this research pillar, which forms as an introduction to the topic itself. But I think most importantly is this paper right here, which you can find online on our website. So let's dive in. Essentially, causal deep learning, the name says it, is based on causality. And we're talking about causality specifically introduced by Judea Pearl and collaborators. And causality has some amazing potential, right? But we see limited adoption in the real world. And there are a couple of reasons why this is the case. And the first one is causality typically requires a set of very strong assumptions, such as knowing a causal graph, knowing structural equations, etc. Plus, parametric forms are typically not very well discussed in causal literature. And I'll show you in a second what I mean with that specifically. And there is no intermediary step between knowing the causal structure and not knowing it. So we want to leverage at least the limited knowledge that we already have about our causal system. For example, maybe we do know some causal links, but we have no way of currently adopting those in methods that we want to use to solve real-world problems. So what about causal deep learning then? So how does causal deep learning tackle these limitations? Well, as we'll see in a sec, causal deep learning allows flexibility on assumptions. So we actually have a way to dial up or dial down assumptions that we make with some effect, of course, but that's fine typically. We base causal deep learning on deep learning, which makes sense given the name. And deep learning is all about parametric forms. So all of these architectures where we go from huge transformer networks to maybe small multi-layer perceptrons, etc. But also, and we want to include this, is stuff like linear regression, good old linear regression, or random forest of all that sort of things. And we want to leverage plausible or partial causal structure. And we show a few ways how you can do that. So with this paper, we want to provide guidance through a very clear definition of what we mean with causal deep learning, as well as introduce a framework to think about causal deep learning and its impact in the real world. This is a very high-level definition in pink, which I'll read to you now. So essentially, causal deep learning studies deep machine learning models that leverage causal knowledge, where causal knowledge is either learned or given and expressed using structures, as we know, like graphical models, functions, such as structural equations, and time, allowing methods to complete certain tasks, such as prediction, forecasting, generation, all your typical machine learning objectives. And what we see is if we look at the state of literature right now, we already identify some areas where causal deep learning has made impact. And this is just a small subset, right? But we already include like 40 papers on this at the moment. And a first one could be imputation, where you define interaction effects with missingness and covariance. And I know present in the panel today, like Dr. Cheng Zhang and Dr. Simon Woodhead, have actually published a paper on this specifically at NERBS, where they learn structure and input at the same time. But also stuff like fairness, where we identify the sources of unfairness using causality, generalization, where causal DAGs are a good tool to generalize beyond one domain and try to learn models in one, and using the causal structure, try to apply them in different domains. Treatment effects, where the lab has done some great work, but also Professor Sapiro in this panel has published a paper on this recently. Drug repurposing, recommendation, but the list goes on, right? This is just a subset of application areas where we can make some true impact. But the thing is, this table is currently missing a way to truly formalize the methods that are proposed in these application areas. So we want to discuss the methods, compare them in a very structured and very detailed way. So before we do that, we have to give at least some causality recap. So what is causality? Well, the best way to describe it is to first describe what it isn't, right? So statistics, you know these statements where A is independent of B, which also implies that B is independent of A. And causality deals with this a bit differently, where we say, if we know that A is causing B, then we already also know that B is not causing A. So big difference is in statistics, we talk about bidirectional relationships, whereas in causality, we have very directional relationships. And with causality, we can answer a set of questions like these, for example, which you couldn't do from statistics. And let me just select a couple, for example, like the interventional questions, which typically take the form like, if I do A, what would happen to B? Or the counterfactual one where I have a situation where I've observed B and A, and I wonder what would B look like when A was not, like A prime was my A of interest. And we can use causality to answer these things, which is nice. Now, to answer these questions, we need two main ingredients. The first is a directed acyclic graph, which models a distribution as a structure. And a second is a set of structural equations. What do I mean specifically? Well, let's reuse the previous structure where A is causing B. This is a directed graph. It's acyclic because we cannot end up in A once we visited it. And with this structure, we can associate a set of structural equations. And since A has no causal parents, we have to assign some noise to A. So A is this unobserved A, which is a noise distribution. And B is defined using this function, which is called a structural equation, which has two arguments. One, the noise associated with A and with B, and then the actual value we observe for A. With this system, we can answer the interventional question, like if we want to know about B when we do A, well, then we do two things. First, we mutilate this graph, because A is no longer dependent on this noise. We actually have observed A now, we plug it in. And the second step is, with this A, we plug the observed A value into the structural equation, and there you go, we have B now. That's all nice, but we need these ingredients, right? So this is a clear limitation, because usually we don't have access to this. Now, if we take back our definition, then we notice three different axes, and let's discuss those in detail. So the first one is structure. And with this, we already know what it means, some graphical model, and this is a type of graphical model, but we'll expand this to more types. The second axis are the functions. We want to define what types of functions we are dealing with in the specific real-world application, and the functions should model this type of thing. And the third is time, where causes are preceding effects. So this is already an applied structure, right? Because we know that causes precede effects, then there's no need to do some causal discovery because we already know this. Now, given the above, our view is summarized as follows. So we are going to define what form this information takes beyond what is considered now. So not just directed acyclic graphs, but any type of graphical model. Not just non-parametric functions, but parametric functions, noise models, all that sort of thing. We answer which papers fall into what category. So remember the papers we discussed earlier. So how do they do these things? And with our categorization, we look beyond where we are now. So what type of models should we investigate in the future? But most importantly, we characterize real-world scenarios with this. So we want to match a real-world scenario using this formalization to methods that have been proposed or should be proposed in the future. Now, there is another categorization method that we know of, and that's called the ladder of causation, which is introduced by Judea Pearl, of course, which models stuff using these three rungs where we increase in causal knowledge using association as the lowest rung. It's the easiest. We make no assumptions. Interventions, which require structure, and counterfactuals, which require structures and functions. Now, because we want to model our methods using these three axes, these three dimensions, we already see a sort of contradiction with this ladder. First, these are the only two rungs that actually increase the required structural knowledge, which we modeled on this axis. Then this final one is a sort of combination between both, right? We make some assumptions on functions, we make some assumptions on structures, so counterfactual lies somewhere in the middle. And then by adding parameters, we can actually differentiate between models that would have been categorized on the same rung using the ladder of causation. We don't want to do that. We want to make clear what type of system we're in. Like, can we assume the system is linear, or should we move up in the parametric scale? Plus, we also differentiate between time and static models, because time has a very strong influence on what type of model we can actually use, either deep learning or standard statistical models as well. Now, let's dive in a bit deeper. What do we mean with structure? So we introduce in the paper this axis where we increase in structural knowledge, where at the lowest rung we have an unknown structure, which is just let's connect everything, no direction, where an edge, as an FYI, is the edge absence is actually a stricter assumption than edge presence, because while this may imply correlation, correlation could be very little. Moving up, we have a plausible causal structure. So this structure, we have a couple of structures combined here, but they all imply the same thing, which is S is independent of D given C, where in this case, in the paper, you find the example that S is smoking, C is cancer, and D is death. So what this is saying is, well, if you have cancer, then smoking doesn't make a difference to death, which is, of course, a massive simplification, but it's a nice illustrative example. And then finally, we have a full causal structure, right? We can make the same assumption as people do in causality, but we have also included these two, which we can leverage in causal deep learning methods. Then the second axis was the functions themselves. So how do we increase assumptions when we talk about functions? Well, we start with the strict assumption, or sorry, no assumption, which is the non-parametric formulation, which is what people in causality have been using for a long time. So non-parametric, anything goes. This is just a function of X and its noise. And that's it. We have to make this super general assumption because we have no idea what's going on, for example. One level up is we just make an assumption on how the noise interacts with the remainder of your function. And this is an additive noise model, but it could be multiplicative, could be this could be in the power, doesn't really matter. Just we know about the interaction with noise and the remainder of the function. Then one level again is, let's talk about a fully parametric model. So this could be a linear model, which also includes the noise, of course. And then finally, the strictest assumption is we know completely what function we're dealing with, which is a fully known structural equation, which is a very, very tough and very strict assumption. Now, let's add in time and visualize this entire thing again. So with these two axes, we want to differentiate between what we give to the model and what we learn given the data. And in this case, this is labeled as input, data, and perhaps some structure or some assumption, and the representation, which could be the output. So if I learn a causal model, for example, then the representation of my data is the same as my output. And in between, we differentiate between what is temporal and what is static. And we can map methods and models in this way. So we say this example model goes from an unknown structural data set. So we have no idea what type of structures we have, but we do know something about the noise. So we are happy to make a noise assumption. We want to model time. So this is a temporal model, and we map to a causal structure. So this is a causal learning method. Now, let's look at this example in specific. So this is actually a model called KEMA, which is based on a paper by these people. And we want to identify what points in this paper made that they are located on the map in such a way. So for the input, we are given time course data. So we know we're we have a data set of some observations of X, nothing more, no structure is given. So we know at least that we are on the associative or unknown scale. Functionally, they are making a noise assumption. So this thing is particular to the paper, doesn't really matter. The only thing that actually matters is this little bit here, which says that this is independent and additive noise. So we are dealing with a noise model. Why are we allocating it as time? Well, in the paper, they say we consider a dynamical system, which is, of course, a temporal system. What are they learning? Well, they are learning this thing. So a probabilistic model over edges in a network, which in their case is a causal graph. So their representation or output is a causal structure, and functionally they remain in the same case. So again, we model this particular paper as such. So we are mapping a noise model with unknown structure over time to a causal structure, which was this thing here, using the same functional assumptions. Now, time has special meaning in causality. So why are we including time specifically? We did the exercise we did earlier for about 100 papers in our submission or in our paper. And we did this for both supervised learning as well as forecasting, which the only difference really is time. So both with these models, we're predicting a label where the first one takes into account just X and the second takes into account X and T. And notice that there is quite a difference when you look at this visualization of our formalization of causal deep learning. And we see that looking at supervised learning, this top row of causal structure is not really populated, whereas in time it is. So this learns us that time has some special meaning in causality because people are able to take it into account much more explicitly in these papers. And this is sort of you see this as a product in our visualization quite well. Whereas if you look at plausible causal structure, it seems that these methods are, these methods are fairly well populated in this plausible causal structure. So what does this mean for practitioners? Well, essentially it means two things. We want to be very explicit about the input before we actually select models. So we want to make sure that whenever you define your situation, you're selecting the correct model. So the assumptions should match your setting. Otherwise, you're going to end up with wrong or biased predictions. And second, if you want to learn causality or you want to have a particular representation, then again, the model or the method that you end up selecting should reflect this. Then, given these two things, the obvious question is like, what if there is no method that satisfies any of the above? Like, should we just give up? And what we propose in the paper is that, no, you shouldn't, right? For those who have noticed, we saw that the input is the same as the representation. So we map from one situation to the other in a similar way, which allows cascading multiple of these visualizations after another. So say we have a practical problem which requires to do some causal reasoning. It's like imagine some sort of causal bandit or something where when you just want to do causal reasoning, but this causal reasoning method requires a fully known causal graph as input, which we don't have. Well, in the simplest case, we first have to learn that, which you could do with this paper. So this is paper number 15 in our causal deep learning manifesto. But notice that this causal reasoning method assumes non-parametric functions, and this causal learning method doesn't yield this. In this case, we can still do causal reasoning, that's fine, but we adopt this assumption in our practical problem as well. Whereas if we hide this away and we just give this causal graph without making explicit what assumptions that we're making, then we may end up with wrong conclusions. So what does this mean for research? Well, also a few things. Maybe we should let this visualization drive what research we do. Like, this is essentially what we're trying to say here. So is your method usable for practice? Another question. Where do we see gaps in research? So what area is not populated? Recall in supervised learning that we may want to populate this causal rule a bit frequently. Essentially, this all boils down to coming up with good goals. And we can also use our formalization to do this. And using our visualization, we've mapped a ton of different areas in machine learning, including bandits and reinforcement learning, generative modeling, all that sort of thing. Looking back at the table from the beginning of our talk, we can now solve the question we wanted to solve in the beginning, which was, how do these application papers or these impact papers, how do they actually map on causal deep learning? Like, what are they assuming? And notice that we observe ranges from papers with ranges from making unknown structural assumptions to fully causal structural assumptions, non-parametric to fully parametric functions, etc. So we have defined this very clear view of causal deep learning, and with it, we can look at the papers with a very detailed mathematical lens and hope to compare these papers in a better and formalized or general way. So that's it. That's the end of my talk. I just want to leave these links here for you to look at. Hopefully you'll read the paper, and of course we invite any comment or any idea with this. And if you want to share this with me, like, do reach out to this email address, because we do think this is a community piece, right? We wanna share and think with you together about causal deep learning, and I'm very happy to do that.
So now we're going to move to the second part of the session, which is a panel discussion. Joining Jeroen and one of our other PhD students, Christoph, we're joined by three guests from industry. The first is Dr. Cheng Zhang, who's a principal researcher at Microsoft Research in Cambridge. We're also delighted to be joined by Professor Guillermo Sapiro, who is a distinguished engineer and the health AI lead at Apple, and is also the James B. Duke Professor at Duke University. And finally, we're joined by Dr. Simon Woodhead, who's the Chief Data Scientist and co-founder of Eedi. Today's panel is going to be chaired by Mihaela. So Mihaela, please take us away for today's panel. If anybody has any questions for either Jeroen based on his presentation or any of today's panelists, please do ask them in the Slack channel, as we'll be opening up to Q&A later in the session.
So thank you, Fergus. But most importantly, thank you, Cheng, Guillermo, and Simon for joining us today. And as Jeroen has very clearly indicated at the beginning of his presentation, your work is part of this causal deep learning research agenda that we are trying to really engage with in this session today. So let me start by asking you, Guillermo, in which settings and applications do you think that causal deep learning would be especially useful? And are there specific settings or applications where taking a causal approach may provide benefits compared to the standard deep learning approach?
Thanks for the question. I'm sorry, you just put me on the spot first, although I'm the least expert in causal studies from the three panelists, but I'm going to try to answer your two-part question. The second part is easier, and there is a lot of work in the literature on using causal inference tools in deep learning to get more robust, to get rid of confounders, so like things that appear in images but have nothing to do with the object that we're detecting. So there is a lot of work in the literature on saying, I don't care about causality, but I can use those tools. The same way as works in differential privacy has been shown to increase robustness of deep learning, although privacy is not the only goal. So I think your second part potentially is easier. There is another thing that we can talk about, what's very common today on large models, because then you can start discovering things that you didn't want to discover. The first part, I'm very biased, but I think is health. And health and well-being is probably the one of the main challenges of machine learning today. I think almost everything else is, sorry for being redundant, but it's almost irrelevant, almost any other application. I really don't care to make a distinction between cats and dogs. I don't think it's very interesting for me. I think if the biggest challenges are on health and well-being and improving our quality and helping people to get the best of their capacity. Again, I'm biased because that's a lot of what I do in research, and that's also the team I lead. Without diminishing the importance of other applications, for me is the most important. It's hard to do any application if you're not healthy and if you're not trying to do the best of your potential. So that is a big challenge for causal inference, and I think where I want to see more and more applications.
Guillermo, that's fantastic place to jump in and turn to Simon, because I think he will profoundly disagree with you and tell you that education is the most important application one should consider. So Simon,
yes.
over
By
to
the
you.
way, you and I had that discussion. Education is part of health and well-being.
Oh, you've backtracked. Okay.
Yeah, no,
wait,
you cannot be a healthy person if without education. It just doesn't go. But I'm gonna let you answer. But I agree. By the way, my wife is an early childhood educator, so I know. But I actually put that on health and well-being. Education is part of that.
Okay. Oh, fair enough. Fair enough. Oh, that's good. I thought it was going to be a very awkward panel. But no. That's fine. Yeah. So Eedi, we're an edtech startup in the UK. We're very focused really on mathematics and diagnosing where students have challenges in their learning and how we can then intervene better to improve student outcomes. So yeah, we're very interested in the education space. I must say, I'm also interested in the health space as well. So yeah, so we've worked quite extensively with the Microsoft research team, led by Cheng, on the application of different machine learning methods, but more recently, causal methods. And I guess my role in this, I think I can challenge you as well, Guillermo, for being the least informed causal person here. So I'm very much a person who brings the data to the table, which I think is quite an important thing for kind of this reality-centric artificial intelligence, which I know this group is, I think we're all really interested in real-world applications. I guess the other reason I think causal methods could be really important within education and also within health is the importance of human constraints. So this requirement that I can't let things like ChatGPT go wild in Eedi. I cannot kind of subject my student users to that directly. So I need to be able to make informed decisions, but I also need a kind of an element of human in the loop there. So I feel like causal methods can provide a little bit more control and accountability there. And something we've been looking at more recently is the fairness of different models. And I was reading something from the Van der Schaar group about this recently and the importance of interoperability. So we've been working with a few different groups at the moment around trying to assess the fairness of algorithms. And it does seem it's one of these things that everybody wants to do, but from working within a commercial organization, that can be something which is then challenging to make time for. So the more you can have standards that you work around, the better you can, or more easily you can apply things like that. So.
Thank you so much. Thank you so much, Simon. So Cheng, you have been in previous sessions of ours on causality And we couldn't resist but invite you again to join us today. But let me ask you this time something slightly different. So do you think that this causal deep learning is the way forward to incorporate causality into real-world applications? And how do you think about this whole agenda?
I'm a big fan of this. It's like, I think I'll wave a flag on this. So I will not frame ourselves on deep, but I feel to make causal really real world applicable, what we need is like flexibility, scalability, efficiency, and generalizability, right? So we, depend on the application. Like we want the answer in certain time. We want the things to be worked on certain scenario with very, funky data. We know it's not linear, right? So it's about the flexibility, efficiency, and application requirement. And with all these requirements in mind, I just given all the machine learning toolbox we open, I think the shiny one is the deep learning. And I think that's the easiest way and easiest framework for us to take advantage of. I mean, like, especially with ChatGPT, being a person, I feel being this field long enough, like working from LSA to ChatGPT. I mean, like the how impressive, how far deep learning as a powerful tool to different applications. I just feel we cannot ignore it. We need to utilize it to the best way possible to help us to answer all the questions.
Thank you. Thank you. So let me now move to another question, and I'm going to again ask Guillermo to maybe take this one, and then maybe I return to you, Cheng. What key developments are needed to advance causal deep learning and drive real-world adoption, whether it's in healthcare, in education, or any other application that you know about and think about?
Thanks again, and thanks to my co-panelists for educating me. I just want to answer with a comment that we need to be a bit careful with associating causality with deep learning as the only solution. We just got a couple of Nobel Prizes in the last 3 years, and particularly in the last year, on causality with zero deep learning on that. And as you know, we just published a paper where we use standard tools as regression discontinuity, synthetic controls. There is a tendency to jump into deep learning when other tools might be better for the problem. So I want to step back and think about causality and not just causality deep learning. And in particularly, always try the most standard and classical tools before a new tool. And as I say,
I apologize to jump on that, Guillermo, since you were not here at the very beginning when Jeroen was presenting. Jeroen did a little bit of a sacrilege. He included you and your work as part of deep learning. To him, everything is the world of deep learning, but he mentioned specifically your work.
As part of causal deep learning, right? So we also include fully parametric models on the scale, which would allow for linear regression to be part of this.
You convinced us, Guillermo.
That's okay. I just wanted to clarify because I know there is a lot of students, and I often ask in my class, how do you detect a circle in an image? And all of the students answer, oh, you run a deep learning. And I say, have you ever looked at the half transform? I say, what the heck are you talking about? And I say, it's the best tool ever to detect a circle in an image. Nobody's going to beat it. And I say, and then when they learn, they say, wow, I didn't know. So I just want to say, if you're working on causal inference, first start by, if you're about to start by reading a good econometrics book before you even read anything on deep learning and causal inference. That's my recommendation. Now, going to your question, I think observational data, I think in particular in areas like health, it's borderline unethical to run some of the experiments in the way that we're running them just to get control groups. I would love for us to be able to develop more tools, as the people in econometrics have done, on working up with observational data and only target a study for the very few data points that your observational data is not giving you. So very, very small studies. But that I think will be our biggest. And for those in the United States, that's a big initiative by the FDA, how to use real world data instead of running studies. Because of cost and ethics, I would love to see more work on observational data.
I cannot agree more, Guillermo. We are also big fans of econometric literature and try to deep learning, to give it a deep learning spin. Maybe that's less on point, but trying to play with synthetic controls and deep learning. So completely agreed on that. Cheng, would you like to also answer this question?
I want to comment a little bit. So I feel, like deep learning is a useful tool we should never ignore, but I feel causality is a field. A lot of this is about assumptions. And I really like Jeroen's presentation because it is about given application, given the need, we need to translate to what we can assume. What type of, if application, if you look at it, it's all linear, like why do you need deep learning? But I feel the most important thing is figuring out assumptions. Functional assumption is one type of assumption. Sometimes can you assume certain structural knowledge already? No. So these are all depends on the application needs. And I think to understand most about causality is be very rigor about application, understanding the application need and translates it into assumptions and thinking about what you can claim. But then on research-wise, I still stand my point is like for a large range of applications, the flexibility and generalizability of deep learning, it is a super powerful tool. And I feel for causality people, culture-wise, I do believe there is a certain, beauty on causal and the theory, but I think we should also just put a lot of attention on the real-world empirical results. And I really believe, in a little bit, I believe the deep learning field with this empirical results-driven spirit, if we only care about it, that's bad. But I do feel this is a very important thing, especially when it comes from application. Commenting, sorry, just that's the previous comments. And then when it comes to what needed in the causality research for more real-world impact, I do feel there are two things, or just three. So if we want something to be used in real world, first, as researchers, we need to know this thing is correct thing to use. So I think there are still a huge effort needed in the research, right? It's a correct method in whichever situation, we remove some ridiculous assumptions. So machine learning or even theoretical research, there's algorithm research, that requires, software engineering efficiency, a lot of deep learning architecture. I think it's algorithm to fulfill certain need. And the next one is user interactions. Causal is something, I think that's not as classic cat and dog as easy to explain. We need to, in some way, people how to understand the result, how to set the prior, how to be able to, have this conversation for people can translate what they believe the domain expert into a machine learning formulation type of assumptions, and also how to communicate the results back. What does the result mean? These concepts, sometimes it's very easy to misunderstood sometimes. So I really want to also really call out the human factors and communication and interaction part.
Wow, I could not agree more. So interesting. And actually, to some extent, Jeroen tried to create this map, this what he calls the topographical map of causal deep learning, partially to show that there are big regions in the map that have very few papers. So there are some regions where there are many and some where there are very few. So I guess part of the effort was try to say, these are areas we need methods for and we need the community to think about. And another thing that we hope you all will engage with, which is also related to what you were saying, Cheng, was at times maybe we can use concatenation of methods on top of each other to conquer some of these areas. So maybe that also relates to what you are saying, as we are developing software and we build maybe open source communities, we can have better ways to kind of join forces and build these techniques and technologies together. On a related note, I have the next question, and I'm going to put you on the spot, Simon, but then I want to ask it to everyone. So In the short term, do you think it will be more powerful to leverage causal deep learning to encode known causal relationships, things we know are causally related, or rather to discover new ones? I don't know whether you have a particular thought about that, Simon, and then I will ask Guillermo and Cheng.
I'm trying to think if I understand this. So to discover known causal relationships.
So you could either assume that these causal relationships are known. We know that, for instance, smoking causes cancer, or and such knowledge, or certain interventions in education, we may know that they are causally linked. Shall we exploit those in the short run, or directly go and maybe learn potential partial causal structures?
Yeah. Okay. So I was really interested when you were talking about the partial causal structures, because I think Jeroen mentioned that we had done this work with Microsoft about learning links between. This was actually links between topics in education, so mathematical topics. So how do we think these topics are learned, cause one another? So can I understand this topic without first understanding that topic? Is there some sort of causal relationship between them? And we are actually doing something at the moment, taking that a little bit further, looking at the causal relationships between misconceptions that students have. So is it possible that students are prevented from learning a new topic because they hold these misconceptions, these existing misconceptions? And can we then look at the strength of those causal relationships, and by doing that, then identify the best misconceptions for a teacher to focus on when they're resolving students' learning challenges? So we are very interested in the kind of discovery of unknown relationships. Obviously that's incredibly challenging in terms of validating the models. So that was something we worked on a bit with a competition at Europe's 2022. And I think this is on a point Guillermo made earlier, and this is the challenge of running experiments and the ethics of running experiments. Literally just today, I was talking to a third party that's advising us on the ethics of running experiments on our platform. And so we're keen to engage with researchers and allow them to run small experiments on the platform. But in order to do that, we require them to sign up to an ethics, a particular framework, and we have a committee that then evaluates whether that would be met. But it is a long, challenging process to do this. You've got to be very careful. Whereas we have tons of observational data. So if anybody wants that and can do something useful with that, then we collect that all the time. So
maybe I go to you first and then to Guillermo, since I think you and Simon have worked together on this. So maybe
I just shared the link of the computation and want to call out, everyone talk about how difficult it is to get data set in causality. And this is a real world data set. We actually did A/B testing. And so I just really want to call out the data set very valuable. And then, as Simon already touched from the education perspective, I was just thinking with my more machine learning hat on. So I think about, discovering new knowledge and using knowledge, I think causal discovery, doing the first traditional causal inference, doing another. But I actually don't see the boundary as 0, 1, because these are just assumptions. You can assume that, you can assume SEM, but you can also assume dynamics. You can assume functional relationship. These are just depends on the application. You want to see how strong or how weak is the assumption, whether this assumption makes sense, how this model is useful to some degree when it's only fitting the application needs. And then I also find it's actually extremely rare if you get application want to completely discover new structure and knowledge from scratch. It's like, I got the whole table from Mars. I have absolutely no idea. So I feel for most real world need, it's always partial knowledge. So we always know something. Even for the education one, we know the grouping, we know partial of the graph, we want to discover the relationship between topics. So I feel what's important is really getting everything we know a priori and be able to encode everything we know in the model. Quality is a huge search space. We can make the problem way easier, make the performance way better. If we just trying our best to take advantage everything we know, and then be able to enforce the model to at least utilizing the null part information for the unknown part, because then if we ignore the unknown part, then that's a very strong assumption. If we can relax this assumption, that's require discover partially new knowledge. And so I see it's not binary, but rather continuum and try to get the best from everything we know.
Thank you. Guillermo, your thoughts on it?
It looks like you put together a panel that we agree. So maybe it's less fun for the audience, but it's fun for us. I want to put a twist on that and add the actionability to your question. And the reason, let me just give you two examples. One is if one disease is hereditary, like even cardiac disease, what can I do? I'm going to change my parents. If I find that causal relationship, it's good to know, but there's not a lot of action in, there is on preventive, hey, you know that you have a predisposition, but I cannot stop that because I cannot change who were my biological parents. On the other hand, walking helps in almost everything, including in education. Exercise, work helps. Do we care really if there is a causal relationship between exercising and improving education? Or the correlation is enough for us because it's actionable? I can encourage you to walk, to exercise. So I just want to add to your question the twist of actionable and say, let's just go and discover things that we can help you improve, get better, or change. That should be, or to confirm them if we are already suspicion. And I would like us to focus a bit less on the important intellectual question, but I cannot do anything about it. Like, as I say, I pick cardio because that's one of my genes. My father died from a heart attack. So there's not a lot I can do. I got that gene. I got a lot of good things from him. I got that bad thing. What can I do? That will lead me to exercise more and be healthier, but I cannot change that. I can do correlations and not causation. Anyway, actionable is for me an important word to add to
very
those
important.
questions.
Yeah, very, very important. Very interesting. Thank you so much. What I'm going to do next is I'm going to surprise one of my own students and kind of put him on the spot to see if he can elucidate, because I think in Jeroen's presentation, he went a little bit fast on that. So Christophe, you are also co-author of this work. So I wanted to ask you how the different ranks of my former colleagues at UCLA, Judea-Pearl's ladder of causations are mapped into this topological map of causal deep learning that Jeroen introduced, and why there is no counterfactual level included on the structural scale. Can you please comment on that more technical part? Because I think Jeroen went very fast and that may be unclear to many.
Yeah, sure. So first, we have to see that Pearl's ladder of causation categorizes model on the basis of the type of query they can answer. So going from the lowest rank, we can answer the question, what if I see something? Then we can answer the questions, what if I do something? And finally, at the highest rank, what if I have done something? So this ladder very correctly shows us that to answer more complicated queries, we need more knowledge. However, it doesn't tell us exactly what kind of knowledge we need. So what our maps does, it shows that there is this structural causal knowledge we might need, and also there is this knowledge about the equations. So when we look at the ladder, the lowest rank, so rank 1, can be easily mapped to our lowest level on the structural scale. So when we have no information. However, then Pearl's ladder jumps straight into interventions, which requires structural causal knowledge, which is quite big assumption. And there is still a lot of things we can do with something in between. So for example, we might have access to some independent statements or maybe to some probabilistic graphical model, which we can use to improve our models. And there's really no place on Pearl's ladder to put these kind of things. So that's why we call it rank 1.5. And then we go to the second rank on the Pearl's ladder, which can be mapped to our third level on the structural scale. So when we want to answer interventional questions, we need the structural causal knowledge. And then when we go to counterfactuals, we need the structural causal knowledge, but also structural equations. So we don't actually need more knowledge about the structure, but we need some more assumptions about the actual equations. So that's why we put it into the same level on the structural scale, but then we differentiate it by requiring strong assumptions on the actual equations. And yeah, the ladder obfuscates like the difference between these two things, and we hope our map actually clarifies what kind of assumptions we need.
Thank you. But most important, thank you, Cheng, Guillermo, and Simon. I will let now Fergus get questions from the audience. Inclusively, some of the questions are for you, the panel. So Fergus.
Thanks, Mihaela, and I'd like to just echo those thanks to Guillermo, Simon, and Cheng. So the first question I think is for the panel from HUD. HUD asks, what are some of the low-hanging fruits that causal approaches can solve to convince people in healthcare to adopt real-world AI solutions?
Could I jump in, Guillermo, and propose something to you, see if you agree or disagree with me profoundly?
Go ahead, yeah.
So two topics in which I think we could show some value, and these were mentioned by both you and Cheng. One of them is this idea of generalization. So often in the type of problems we tackle in our lab, when we work with clinicians, they want to know whether some of the predictions and forecasts we make in one population will translate to another. And both you and Cheng mentioned generalization. And we feel that this causal deep learning could help improve generalization across these different domains. Another one, which I think everyone has worked on this panel, inclusively ourselves, but all of you, relate to imputation. So often one may need to be careful how one imputes if in a clinical setting, and be careful with that. That may look like something auxiliary, but we often felt that this may corrupt the data in horrible ways. I don't know what you think, Guillermo.
I agree with both points. I'm going to go a bit lower hanging fruit potentially without giving the answer. And I will go back to my question. That's why I appreciate, because it gave me time to think. I will be looking for something that is relatively easy to intervene, relatively easy to find an action to change that, and then show with causal inference that we discovered that action and the impact that we wouldn't have discovered with any other tools outside of A/B testing or stuff like that. So I'm thinking about the paper we published in Mihaela's workshop last December is one such example. It's a very simple nudge, and it's hard for me to think about any tools not from causal inference. You know, we use one tool, but there might be others that could really prove it without having to run a study. So I would say, if you are going after showing the value of causal inference, try to pick something that is so actionable that people will love it, and we say, okay, you prove it to me. And then what Mihaela says is more fundamental. I was just going very practical. And you know, if you prove in causal inference that going to sleep every time at 10 o'clock really changes your education, that's not a very hard thing to do. Although, unless you're a teenager, biologically, you cannot go to sleep early, that has been shown. But Yeah, just pick something that is a very actionable thing, and then people will love it, I think.
On that note, it was a workshop that I organized together with Cheng here and Jeroen, so we call it causality for real-world impact. So Guillermo had a paper in that workshop, and there were quite a lot of interesting other papers. So if you want to look at it, please do. And also some shameless advertisement, Fergus. Cheng and I, as well as Dominic, organized this CLEAR conference in April, which is a related conference to this discussion, and I hope many of you will attend.
And I'm gonna follow your shameless. In that conference, my team at Apple published a paper on imputation for causal inference. So exactly on your point, So yeah,
that's
Andy
what we
Miller
share.
and
That's
others.
what we all share, everyone.
Yeah.
Fergus, sorry for we are stopping the advertisements now.
No. I think that's great, and I think a lot of perspectives for some people to think about if they're thinking about taking these things and trying to bring them more into reality. Unfortunately, I think in terms of time, we're probably running out of time for any more questions now. But there's a couple more on the Slack channel that we'll try and take offline after the session and respond there. I do want to thank Simon, Guillermo, and Cheng once again for that fantastic panel discussion. Hopefully everybody enjoyed it as much as I did. Before we wrap up,
yes, thank you.
You guys are more than welcome.
Thank you.
Before we wrap up, I'd like to pass over to one of the other postdoc in our lab, Zhaozhi Qian, who is going to give a quick update from the last inspiration exchange session where he presented and talked about Synthcity, and give a brief update on that project for everybody.
Great. Now time for a quick update on the Synthcity library. And Synthcity library is a open source software released and maintained by our lab that is aimed to democratize the cutting-edge research in synthetic data and generative modeling for different use cases like privacy, fairness, augmentation, and transfer learning. If you're interested to know more, we have a previous inspiration exchange that is dedicated to this topic. Although February is a short month, we have made a lot of development progress in the library. One of the biggest things is that the much requested image generation pipeline is now available in beta, and we have capacities now to loading and handling image data with different type of image generators with also privacy guarantee. And we have also added quality evaluators and metrics to evaluate the images. There are also improvements on tutorial and documentations. And here we want to thank all the community contributors for making pull requests and release issues. Now going to March, we're going to add an entire new benchmark for synthetic data augmentation related tasks that allows one-click benchmark and applications in augmentation, transfer, and fairness. We'll also add a few plugins and metrics, including the two recent work from our lab, Lomias and Google, which are respectively about membership influence attack simulation and to generate more higher fidelity tabular data with a GNN-based generator. Finally, to further engage the community, we're also announcing a developer program. This is especially for students or early stage developers who want to get more experience in open source development. We are very happy to acknowledge your contribution and provide a reference if you have contributed a significant amount of code to the Synthcity library. And we have similar initiative to encourage contributions in documentation and tutorials. And last but not least, we also created a Slack channel to enable further discussions on, and the joining link can be found on GitHub. Thank you for.
So no, just to wrap up briefly, if you enjoyed today's session and discussion and have any colleagues or friends that perhaps missed it, we will be placing today's session on YouTube soon, so keep an eye out for that. And we hope as many of you as possible will join us for our next session on the 21st of March where we'll be discussing machine learning for next generation clinical trials. If you haven't done so already, please do sign up to Inspiration Exchange using the link on the slide to keep up to date on all of the developments. And finally, a big thank you to both our panelists and presenters, but also to everyone who joined us today.